Hi, and welcome to 5.2 Kinetic Friction and Internal Energy. Hopefully you tried this video out on your own, read the example problem. Let's get right to it. Number one, when an object moves at a constant speed against friction on a horizontal tabletop, there is an increase in the object's blank. All right, so a couple of things. It's moving at constant speed. It's going against friction. And they're looking for an increase in something. Inertia. Let's talk about inertia. Mass is a measure of inertia. Is the mass changing? No. So is the inertia increasing? No. Okay, kinetic friction. Kinetic friction actually doesn't change unless you change the normal force or you change the surface, the two surfaces that are interacting. So we're not changing the weight of this, object, and we're not changing the surfaces. So kinetic friction, nope. Temperature or acceleration? Well, let's look at acceleration first. It's going at a constant speed. So is it accelerating? No. How could the temperature be increasing? What's happening here is since there is friction, there's an increase in internal energy. That's the second part, internal energy. Okay, so anytime there's friction, you're going to get some heat. You're going to gain some internal energy. You're going to increase the temperature. You could try this by putting your hands together and rubbing them together for like 30 seconds. Now be careful because you might burn yourself. Well, not really. But it gets really hot. You could feel the friction between your hands causes increase in temperature. So increase in internal energy. Try it out. Rub your hands together really fast. Number two, a car's performance is tested on various horizontal road surfaces. The brakes are applied, causing the rubber tires of the car to slide along the road without rolling. The tires encounter the greatest force of friction to stop the car on dry concrete, dry asphalt, wet concrete, or wet asphalt. All right. We're looking for the greatest force of friction. We're looking for the most friction. All right. We could probably eliminate a couple things already just from common sense and real world experiences. Anytime the road is wet or if it's covered in ice, it's not going to have as much traction. You're not going to have as much friction between your tires and the road. So if we want the greatest force of friction, we want dry roads. Now, is it dry concrete or dry asphalt? You can't just guess. You have to look in the reference table. It's like, well, I've touched concrete before. No. So you look here. Dry asphalt. We're looking at these two guys. Rubber on concrete, dry. Right here. What happens is the greater the coefficient of friction, the more frictional force there is. So you can see both the kinetic and the static are greater for concrete. Dry. And if we wanted to confirm what we said before, we're looking at wet. Yep, that's much less. And that's much less. So the concrete dry, that's going to be the highest number for kinetic and static. So we'll go like this. We want to do dry concrete. Why do you think so? Highest coefficient of friction, mu. Number three. A wood block containing 50 newtons is at rest on a wood table. According to your reference table, what is the minimum horizontal force needed to start the block in motion? And what is the minimum horizontal force needed to keep the block moving at constant velocity? Okay, so first thing we want to look at, what kind of materials are we dealing with? It's wood on wood. So we look at our reference table, get rid of this stuff. Wood on wood is going to be right here. For kinetic, it's 0.3. For static, it's 0.42. Let's write that. For kinetic, it's 0.3. For static, it's 0.42. They're saying what is the minimum horizontal force needed to start the block in motion? So it's at rest. So we want to start it moving. We're going to be looking at the static coefficient of friction. So FFS is equal to mu S Fn. It's just the coefficient times the normal force. And luckily, they tell you, they don't give you a whole lot of space here. So you have the normal force is equal to the weight, 50 newtons. So 0.42 times 50 newtons. We could draw a quick free body diagram. How do you know? How do you know, Mr. Nangle? How do you know? Well, if the Fg is equal to 50 newtons, the normal force is equal to 50 newtons. In this case, they're equal and opposite. So the static coefficient of friction is 21 newtons. All right, so it takes 21 newtons of force to start this block moving. Once it's moving, it says, what is the minimum horizontal force needed to keep the block moving at constant velocity? If you look at the top, it's this situation. You want an applied force that's equal and opposite to the frictional force so that the forces are balanced, meaning there's no net force. We don't want a net force because we don't want an acceleration. We want constant velocity in this case. So we want the forces to be balanced. So if they're asking what is the horizontal force needed to keep the block moving, they're looking for FA, and I'm running out of space here, but that's FFK against the frictional force. So you just figure it out. You go F equals mu Fn, but in this case, we're looking at the kinetic friction because it's moving. Anytime it's sliding, it doesn't matter if it's constant velocity, doesn't matter if it's accelerating. In either situation, since it's moving, it's sliding, we use the kinetic one. If it was at rest, we'd use the static one. So since it's moving, FFK is equal to 0.3. Remember, you're looking at the kinetic coefficient of friction. Don't plug in the static one. And the normal force stays the same. So the frictional force that we need to balance out is 15 newtons. So if the frictional force is 15 newtons, and that doesn't change, by the way, unless you change the materials or the normal force, the kinetic friction stays the same. So if you apply 15 newtons this way, those two forces are balanced, and you'll be moving at a constant velocity. You won't have a net force because they balance each other out. They cancel each other out. Okay. For number 4, it says a 0.17 kilogram rubber hockey puck is at rest on an ice rink. What is the minimum horizontal force needed to keep the puck moving at constant velocity? So the mass is 0.17 kilograms. We want to move it, and it's rubber on ice. So the coefficient of kinetic friction, let's see, rubber on ice. Rubber on ice, that's going to be right here, 0.15. Pretty low coefficient, relatively speaking, because it's on ice, 0.15. There's not a whole lot of friction happening there compared to like dry concrete and rubber. So what is the force needed to keep the puck moving at a constant velocity? They're technically looking for the applied force. And in order to find that, we would need to know what the frictional force is that we need to balance out. And to know that, we need to know what the normal force is. And to know what the normal force is, we have to figure out what the weight is, Fg, because they tell us what the mass is. Let's put all these forces into a free body diagram, see if we can make it a little clearer. So this is the force due to gravity pulling you down, pulling the puck down. And the ice is exerting a normal force back up on the puck. Those two things are equal to each other. Now, we want to move the puck this way. We want to apply a force. And we want to do so that it moves at a constant velocity, so that applied force better equal the frictional force between the two surfaces. So if we figure out what this frictional force is, we know what the applied force is going to be. But before we could do that, right, because we want to do FF equals mu Fn, we're going to run into a roadblock. Because even though we know what the kinetic coefficient of friction is, 0.15, we don't know what the normal force is. So let's figure out the normal force first. Again, the normal force is equal to the weight. So if we do Fg is equal to mg, Fg is equal to 0.17 kilograms times negative 9.8 meters per second squared. Fg, the weight of the puck, is 1.67, so we can round that to 1.7 newtons. So this is 1.7 newtons downward, negative. So the normal force must balance that out. 1.7 newtons up. So now we plug that in here, and you get a frictional force of 0.25 newtons. So since the frictional force, and you could call it FFK or just FF, since this is 0.25 newtons, that's the frictional force that's going to oppose you no matter how hard you push on the puck. It's always going to be 0.25. So if we want it to move at constant velocity, you have to balance that out, 0.25 newtons in the opposite direction. Okay, moving on. So that's the answer. FA equals 0.25 newtons. Okay, number 5. An applied force is used to keep a 10 kilogram block of unknown material across a horizontal surface whose material is also unknown. The frictional force acting on the block is 55.86 newtons. What is the coefficient of kinetic friction between the block and the surface? Interesting. So they don't tell you it's like wood on wood. They don't tell you it's copper on steel. They're looking for the coefficient of friction, the coefficient of kinetic friction technically, because you're moving. So they also tell you enough information to calculate this. Don't get nervous and figure, oh man, what's the reference table doesn't tell me this unknown material. They always give you enough information to figure it out. So the mass of the block is 10 kilograms. What else do they tell you? The frictional force. Oh, wow. So they tell you the frictional force is equal to 55.86 newtons. And it's moving, so it's kinetic friction, which makes sense because they asked for the coefficient of kinetic friction. So again, we want to try to use the friction formula. FF equals mu Fn. So they tell you this is 55.86 newtons. We're looking for the coefficient. We don't know what that is, but that's okay. We could solve for it if we know what the normal force is. Now they tell you the mass of the block, so you have to find the weight first. Fg is equal to mg. Fg is equal to 10 times negative 9.8 meters per second squared. So the weight is equal to negative 98 newtons, which means the normal force is equal to positive 98 newtons. If you look at our free body diagram from above, it looks the same. Instead of 1.7, it's 98. And the normal force is equal to 98. You plug it in right there. So now the coefficient of friction, which by definition is the ratio of the frictional force to the normal force, you just do 55.86 divided by 98. And you get 0.57. Now there's no units on this because this was a newton and we divided it by a newton, so the units actually cancel out, so you get 0.57. Then it says, according to your reference table, what material could the block and surface be made of? So you look in your reference table, we're looking for 0.57. So what's close to 0.57? Let's see. Not that. Oh, wow. This is pretty close, right? So I thought maybe 0.58, concrete, wet concrete and rubber. But if it's steel on steel, that's even better, right? So that's the best answer we could say, steel on steel. Steel on steel. The coefficient of kinetic friction is 0.57. Very nice. Number 6 says, a 15 Newton horizontal force is needed to keep an object weighing 30 newtons moving at a constant velocity of 2 meters per second across a horizontal surface. Is the force of friction acting on the box static or kinetic? We should know this already, right? It's moving, right? Keyword, moving. So kinetic. It's not stationary. It's not static. It's moving. What is the magnitude of the frictional force acting on the block or on the object? We could draw ourselves a free body diagram to help explain this, right? So Fg, there's a weight pulling you down. There's a normal force pushing back up. It's a level surface. And it says a 15 Newton horizontal force is needed to keep an object weighing 330 Newtons. So if this is 30 Newtons, this is 30 Newtons, I'm applying a force of 15 Newtons. And it's moving at a constant velocity. So there must be some frictional force. Now, since it's moving at a constant velocity, that means it's not accelerating. And if it's not accelerating, that means the net force must be 0 newtons. And if the net force is 0 newtons, remember, net force is just the sum of all the forces. In the y direction, the 30 Newton forces cancel each other out. And in the x direction, if you're pulling with or pushing with 15 newtons and you're moving at a constant velocity, the frictional force must also be 15 newtons because the forces are balanced. You have no net force. You're not accelerating. You're moving at a constant velocity. So you don't have to do any work for B. It says, what is the magnitude of the frictional force? 15 newtons. If you're applying a force of 15, that's equal to the frictional force. For C, it says, what is the coefficient of kinetic friction between the object and the surface? They don't tell you what type of material it is, wood, steel, copper. But again, they tell you enough information to calculate the coefficient. So we're looking for the coefficient. They tell you, so let's just use the frictional formula. FF is equal to mu Fn. This was a very scaffolded question. B tells you that you have to know that the frictional force is 15 newtons given this information. And mu is what we're looking for. And the normal force is equal to the weight, 30 newtons. So the coefficient is just 15 divided by 30, which is 0.50. And there's no units. So that's the kinetic. And again, it's kinetic. We know it's kinetic because it's moving. Kinetic coefficient. All right, number 7. When a 25 Newton horizontal force is applied to a 100 kilogram wooden box on a horizontal wooden tabletop, the box remains at rest. Interesting. It's at rest. Is the force of friction acting on the box static or kinetic? What do you think? Hopefully you said static. It's stationary. It's at rest. It's not moving, so it's static. The little trick from the last homework was I did static like this, and then you could kind of make the C into an O, stationary. Little trick to remember how to do that. So when is it static? When it's stationary. If it's at rest, it's stationary. B, what is the magnitude of the frictional force acting on the object? Okay. Let's draw ourselves a free body diagram. What information did they actually give us? We have a weight and a normal force, and what's happening? 25 Newton force is being applied. So FA is 25 newtons, and it's a 100 kilogram box. So that's enough information to find FG. The box remains at rest, so we know there's a force of friction opposing this applied force, and we said it's the static force of friction because it's not moving, and we don't know what that is yet, but we can figure it out. That's what they want to know. Okay, so before we do that, we want to do FF equals mu Fn. Hopefully by now you know you can't just start with that when they give the mass, because we're looking for this. It's a wooden box on a wooden tabletop. We forgot to write that down. So the static coefficient for wood on wood, look it up in your reference table. It's equal to 0.42. Remember, it's static. So don't use the kinetic one, not 0.3, 0.42. So 0.42 here. 0.42 here. Again, we don't know what the normal force is yet because they tell us what the mass is. So we have to do Fg is equal to mg first. Hopefully you did that first instead of like working backwards like this. Times 9.8 meters per second squared. So Fg is equal to 980 newtons. So the normal force is equal to 980 newtons as well, because they are balanced out in our nice free body diagram here. This one's going down, it's negative. All right, so now we're ready to do the multiplication for the static friction. You do 0.42 times 980, and you get 411.6 newtons. Okay, 411.6 newtons. All right, that's about it. Have a good day.